Hello everyone, myself Dr. Ranjana Gogoi, Associate Professor of Statistics working at Gorgaon College. In this video, I am going to present the second part of the simple linear regression model. In the earlier video, in the part 1, I had introduced a two-variable regression model, which is generally known as simple linear regression model, how the model is constructed, the assumptions attached with the simple linear regression model, and how to estimate the unknown parameters beta naught, beta 1, etc. and sigma square from the available sample observation. In this presentation, I shall try to explain how the hypotheses for parameters are tested and about the building up the confidence intervals of the parameters. Hypothesis testing is an essential procedure in statistics. A hypothesis test evaluates two mutually exclusive statements about a population to determine which statement is best supported by sample data. In order to test H0, that is a null hypothesis, we must calculate a test statistic, which is a random variable that has a known distribution when that null hypothesis is true, and some other distribution when the null hypothesis is false. If the value of this test statistic is one that might frequently be encountered by chance under the null hypothesis, then the test provides no evidence against the null, and then we have to accept the null hypothesis. On the other hand, if the value of the test statistic is an extreme one that would rarely be encountered by chance under the null, then the test does provide evidence against the null hypothesis. And if this evidence is sufficiently convincing, we may decide to reject the null hypothesis. So, for any empirical data, we usually set up a hypothesis such that H0, that is beta 1 equal to 0. Here beta 1 is the slope coefficient, and here we are assuming that the slope coefficient is equal to 0, which states that there is no linear relationship between y and x in the model. Our simple linear regression model was that yi equal to beta naught plus beta 1 xi plus epsilon I. Here we have n observations, n pairs of observations xi, yi. So we are getting n such type of equations. Here I takes the values 1 to 3 up to n. So in order to obtain a test for beta 1 equal to 0, we assume that yi follows normal distribution with mean beta naught plus beta 1 xi and variance sigma square. Here this variance sigma square is constant and mean of y is beta naught plus beta 1 xi. Then beta 1 cap and sigma square have the following properties. So beta 1 cap follows normal distribution with mean beta 1 and the variance sigma square by summation I from 1 to n xi minus x bar whole squared. This is the variance of the estimator beta 1 cap. And the ratio of the sample variance S square and the population variance sigma square follows chi-square distribution with n minus 2 degrees of freedom. So these are the properties of beta 1 cap, estimators, and sigma square. And the beta 1 cap and S square are independent. So now the null hypothesis can be tested by confidence interval with the help of t-test approach. As Beta 1 follows normal distribution. Therefore, we can set a new variable z such that z is equal to beta 1 cap minus beta 1 divided by standard error of beta 1 cap. So here, here define z statistic. That is the, here this is beta 1 cap is the estimator of the beta 1. So this is the parameter, estimator minus parameter divided by the standard error of the estimator beta 1 cap. So this is a standard normal variate. There will be a standard normal variate and it will follows normal distribution with mean 0 and variance 1. And if we put the values for standard error of beta 1 cap, then we get the statistics like this, 3. So here Z is standardized normal variate, hence we can use the normal distribution to make probabilistic statement about beta 1. And provided the true population variance sigma square is known. If the value of sigma square is known, then our statistics will be like this. So there is an important property when sigma square the population variance is known. That is that a normally distributed variable between mu and variance sigma square is that the area under the normal curve between mu plus minus sigma is about 68%. Between the limits, mu plus minus twice sigma is about 95%. And that between mu plus minus twice sigma is about 99.7%. So it is very important property for normal curve. But in general, sigma square, the population variance is not known. And in practice, it is determined by its unbiased estimator, smallest square. The smallest square is the sampling variance calculated from the sample observations. So now we replace sigma by smallest, then Z statistics become T statistics. If you replace sigma by smallest, that is the sampling variance, then Z becomes T statistics and it can be written like, so T becomes like this, beta 1 cap minus beta 1, standard error of beta 1. In the denominator, the standard error of beta 1 cap, sigma is replaced by S small s. So the T variable defined above follows student T distribution with n minus 2 degrees of freedom, and then we can test these T statistics accordingly. If a specific value of beta 1 is given, suppose beta 1 star, then our null hypothesis become beta 1 equal to beta 1 star, and then the test statistics becomes T equal to beta 1 cap minus beta 1 star divided by standard error of beta 1. And it also follows T distribution with n minus 2 degrees of freedom. There is a shortcut rule of testing of hypothesis, 2T rule of thumb for testing significance. So there is a shortcut rule to test the hypothesis. We stated that if the number of degrees of freedom is 20 or more, that is n minus 2 equal to 20 or greater than 20, and if alpha, the probability level of significance, is set at 0.05, that is, if the probability level of significance is 5%, then the null hypothesis beta 1 equal to 0 can be rejected if the T value exceeds 2 in absolute value. If the value of T is greater than 2, then for null hypothesis beta 1 equal to 0 can be rejected if the degrees of freedom is the value for degrees of freedom is 20 or greater than 20 and the level of significance is 5%. This is a shortcut rule for testing hypothesis of the parameter values. Now we have to build confidence interval for beta 1. By using T distribution, the confidence interval for beta 1 can be constructed like this. This probability of T lies between minus T alpha by 2 to T alpha by 2 is equal to 1 minus alpha. Here, this T value is nothing but the value given in 4, that is beta 1 cap minus beta divided by small s divided by square root of summation xi minus x bar whole square. And T alpha by 2 is the value of T variable obtained from the T distribution for alpha by 2 probability level of significance at n minus 2 degrees of freedom. So this critical value can be taken from the T table at alpha by 2 level of significance and at n minus 2 degrees of freedom. So it is called the critical T value at alpha by 2 level of significance. So after substituting the value of T in the probability term, we get this one. So T equal to beta 1 cap minus beta 1 divided by standard error of beta 1 cap. So this will be like this. And if you rearrange, you can cross multiply standard error of beta 1 cap with minus T alpha by 2 and plus T alpha by 2. So we get this value, and if you take beta 1 cap to left hand side as well as right hand side, you will get this expression for the confidence interval. So this above equation provides 100 into 1 minus alpha % confidence interval for beta 1. And we can write it in compact form also. This is written like this, that 100 alpha 1 minus alpha % confidence interval for beta 1 is beta 1 cap plus minus T alpha by 2 into standard error of beta 1. There are some important features of the confidence intervals. The width of the confidence interval is proportional to the standard error of the estimator. This means that the larger the standard error, the larger is the width of the confidence interval. Or differently, the larger the standard error of the estimator, the greater is the uncertainty of estimating the true value of the unknown parameter. So always for a good precision, we need a small value of standard error. Thus, the standard error of an estimator is often described as a measure of the precision of the estimator. That is, how precisely the estimator measures the true population value. Now, we are going to testing the hypothesis and confidence interval for sigma square, the population variance. We have already found that the ratio of sample variance S square and the population variance sigma square follows chi-square distribution with n minus 2 degrees of freedom. Here S square is the unbiased estimate of population variance of Y, and sigma square is the population variance. If we postulate that sigma square equal to sigma square star, then this chi-square provides a test statistics for H0 as S square is the sampling variance and unbiased estimate of sigma square, where sigma square star is the certain value of population variance which is already given. So for certain probability level of significance, suppose it is alpha %, we can carry out the chi-square test of significance at n minus 2 degrees of freedom and can be tested accordingly. Thus, we get the value for chi-square, calculated chi-square. Now, for constructing confidence interval of sigma square, we may use the chi-square distribution as this. Probability of chi-square lies between chi-square 1 minus alpha by 2 and chi-square at alpha by 2. This is equal to 1 minus alpha. Here chi-square is the value in the middle of this double inequality is given in 1. In our earlier slide, it is given, and chi-square 1 minus alpha by 2 and chi-square alpha by 2 are the two values of chi-square, the critical chi-square values obtained from the chi-square table for n minus 2 degrees of freedom. And if you rearrange this expression 2, then we will get this expression. We are putting chi-square equal to small a square by n minus 2 into small a square by sigma square. And after rearranging this, we are getting this expression, which is the 101 minus alpha % confidence interval for sigma square. So today I conclude my presentation. Thank you.